things that we can do. So let's begin. In this case, I'm going to create a new file, and I'm going to go with a metric part. And what this gives me is a place to begin. So I'm going to take this box command, and I'm going to stick it right on the end, and I'm going to build this 10 by 10 millimeters. And I want that 0 degrees, and let's make it 200 millimeters long. Okay, so this is a relatively stiff shape. The thing you're going to find out about shapes is the further the mass is out from the centroid, the stronger it is. So that's why when you take a look at any kind of a beam or something, if they have to run something through it, they drill the hole in the middle of it, because things in the middle don't add as much strength as things on the outside. So it's very common to have an I-beam shape, because it resists forces in 2 dimensions. So we're looking out for that wind load of something hitting a 100-foot long wall, and we're looking for snow load, rain load, that type of thing. So in this case, I'm going to chip away at this, and I'm going to lock onto this end here. And what I'm doing is I am designing an I-beam. So all the webs are 1 inch, so if it's 10 by 10, so I know I need this rectangle to be about 8 inches long. So that's going to become 8. And if I want 1 inch in the middle and it's 10, that means it's got to be 4.5. And I want top and bottom to be the same distance. So I can go between here and here. And that becomes 1. Okay, now I took a little time to draw that. And it'd be really easy if I didn't have to draw it again. So this is like a quick mirror command. So I'm going to go mirror, and it wants to know what the first point of the mirror line is. So I can mirror right around the center. And it puts the same shape on the other side. So I don't have to do it. Basically, the software is way ahead of me. All right, so now if I come, you see I can, that's my eye that we're going to take. So we're going to take this piece, and I hold the control key down so I pick both of them. And then I can just take this, and I know it's like 200, so I can go like, and so now I have an I-beam, quick and dirty. So in order to find out if this is strong enough, what I'm going to end up doing is to do something we call analysis. So analysis is done in the simulation mode. So I'm going to click on the simulation tab up here. And this is going to be a new study, right? Because We don't have an existing study to work with. All right, it's going to be a linear static study. And our mesh type, I'm going to leave it at tetrahedral. Now, a mesh is, we divide the whole piece up into little tiny segments. And if you think about the little tiny segments as mini marshmallows, anything you do pushing on one marshmallow is going to affect the marshmallow next to it. So everything squishes or bends or twists or pulls. And when you look in the curricula document, all this is in there. And it's on page, well, it begins on page 737. So, you know, if you get to the point where you want to do an analysis on something and just check it out, that's a quick and easy way to say, oh, well, I can do that. So the next thing it needs to know is, well, what kind of material is it made out of? So we haven't assigned a material to it yet. So there is a material table, and there are metals, you know, so there are like aluminum and copper, iron and other metals. There's steel, titanium, zinc. There are non-metals, different kinds of plastics. And you can even create your own materials. And so one of the things that I do is I show everybody a website called MetWeb. I can't even pronounce that. So MetWeb is a collection of hundreds of thousands of different materials. So if you wanted to find out the materials properties for balsa wood, for example, you get 20 or 30 entries, you know, so then you have to break it down to what kind of balsa wood. And, you know, eventually you get very accurate information. So I'm going to do this out of ABS, I think. And let's just apply, you know, so if you look at it, it gives us a density. Thermal expansion, so we know how much it's going to grow and shrink over the course of, you know, a given temperature range. How fast it's going to conduct temperature, right? Metals conduct faster than, say, wood, for example, on temperature. Specific heat, how quickly does it soak in? So when you design a slide for people that's going to be facing the sun, well, then you got to determine, well, you know, how do we shed all that heat? The modulus of elasticity is all about how much will it flex before it you know, KOs itself. So there are all kinds of things that are in these little properties. And so we just apply that to the model, and notice that it changed the color to the color that was showing on that. And so up here, it now talks about, oh, the material is ABS plastic. So I know I'm designing this thing for kids and I'm going to put some weight on it. I want to know how much is it going to deflect and, you know, that type of thing. So the first thing, since space is infinite, and if we were in outer space and you push on something, well, I'm going to go one way, whatever I pushed is going to go the other way. You know, gravity is going to take those two objects and pull them back together. So on the Earth, if we only support one side, we have a cantilever situation where the other end will bend down. If you want it like a bridge and you want it to stay standing, then we have to support both ends. So one end of a bridge is fixed. All right, you know, I want you to think about, okay, we put the bridge there, we build these battered walls, you know, so that's what those sloped concrete walls are called. There's a battered wall. That goes up and that's going to sit underneath and the bridge is going to sit on top of it and we're going to bolt it in there. All right. And so what that is a fixed end. Now the other end of the bridge, it might be 30 feet away on one day. And if we get to summer, it might be 30 feet, 3 inches away. In winter, it might be 29 feet, you know, 5 inches, you know, because it's going to grow and shrink over the course of the year. So we use what we call a roller bearing. All right, so if you ever, have nothing else to do, you can walk under a bridge and take a look at all the various things under a bridge. Fascinating. All right, so over here we have our constraints. So we have a fixed constraint, and it says, are you going to select a face or a chain or something? And what I want to do is select this eye of the end. All right, so I'm just going to select that, and it put in these two elements, which are telling me that yes, it's fixed. And you right click at the end and it says, okay, I'm fixed, I'm ready to go. The other end, this end way over here, I'm going to do something called pin, which allows it to move a little bit. And in order to do analysis properly, the computer needs to know, well, what are the things that are supposed to not move and what are the things that are supposed to move? And let me tell you what's in between them. So again, I'm looking for the eye. And again, you see the two pieces there that says, okay, it's pinned. And you right click to accept it. And so I have a pinned end and a fixed end. And then we have to put some kind of a force on it. So I'll come up to force. And you're going to see that, okay, I can come down here and I'm going to select a face. And I want this top face. And like anything else, if you wanted to put it on a different one, you can slide to the edge and right click and it'll give you a list. Sure it will. Make a liar out of me. It'll give you a list of all the various planes. So I'm just going to come down onto this top and I'm going to pick the top. And incredible lightness of being, this thing is floating up in the air with this kind of a force. So I have to flip it. So on the little toolbar, I can say, oh, let's flip the force direction. And right now we've got 1,000 Newton meters. All right. So basically it's like a kilogram weight on the top of this. It's 200 millimeters long. In the grand scheme of things, that means it's about 8 to 10 inches to, translate into like, okay, I can do something like this. Right. So a foot rule is like 300 millimeters. So, that is like about 8 or 9 inches. All right. So we could even change this value. Let me just move this up to like a, 2,000 Newton meters. And I will just accept that with a right click. And so now we have a force, and you can put lots of different forces on an object and analyze it. The more forces, different kinds of things, the longer it's going to take. We got to mesh this whole thing. So meshing is how small are the little pieces we're going to look at. And now we're looking at defining the mesh. All right, subjective mesh size right now is defaulting to 11 millimeters. Well, the beam is only 10 millimeters wide. So we're going to knock this down quite a ways. And the reason we do that is the finer the mesh, the longer it takes to calculate, but the more accurate it is. So, I'll just say mesh it, and it'll take a little while to do that. And it's created this mesh so we can see. Now, if the mesh is too coarse, when you go to solve it, it says, nah, I can't handle it, and it throws an error. So we got to make sure that it's meshed correctly. And then we can come over to the solve button. So when you think about this, I don't want you to think about this, we designed a piece, we pinned the ends, we put a load on it, And now we can take a look at things. So right now we're looking at the stress. So what this is showing us, the areas in red on either end are the most stressed. Okay, so when you think about it, you know, when something is pinned on each end and we start pushing, you know, it's really right here at the edge that's taking, you know, the brunt of it. It will sag the most in the middle, but the edge has the most force. So we can calculate all the force out, the reactances and everything else. It's really a great, you know, for those of you with physics backgrounds, you can get into all kinds of things on the materials. We can go and see what the displacement is. So you can see now that the center is the furthest away. So we come up here and we see that the very center, they say, is going to sag about 3/4. Ooh.
Everyone's saying, sorry to interrupt, Tom.
Sure.
But right now I just see your beam and it's still in the tetrahedral form and it's white. Do you have something else on your screen?
Yeah, it should be showing as varied colors.
Does everyone see that?
No.
No, I don't see that either.
Okay,
All right,
I just don't go, yeah. So, yeah, I want to see what you see.
All right, so let me see. I'll stop this share. And
Devin, that was a good catch. I was waiting for that to happen, but I guess it was already happening and we didn't know, except for you.
He was describing it. I know what he was talking about. I want to see it too.
oh yeah, you definitely want to see this because it gets cooler as we go. I want to share this screen. And are you seeing it now?
Yes.
It's not colored yet?
It is colored.
Oh, I got two people shaking their heads no. And
no, we see.
I've got multiple screens that are stacked on top of each other.
We see, yeah, we see your presentation. Yeah, we see your PowerPoint right now.
Okay, so let me give that a stop. And that always happens when you have multiple. So let's go for all our smiling faces.
Good.
All right, so are we seeing, okay, we're much more better now, right?
Yep.
Okay. All right, so right now, when it first came up, we were looking at stress. And so you'd see the red on either end. And so that tells us, you know, how much it's really stressing. And then let's go to displacement. And I'm going to slide your faces, much as I love you all. All right, so 0.07 millimeters, this is going to deflect. So it's not going to deflect much with the 2 kilograms of force applied, right? So those 2,000 Newton meters of force isn't going to cause much. You notice that we're about 10% now. So if we do actual, there's not much deflection happening at all, although the colors are telling us where it's going to really stress the most. But with the, you know, looking at it 10 times normal, you really get a chance to see it. Now, once you get to this point, then up here at the top, there's an animate button. So what this allows us to do is to animate the stress. So we can say, okay, as we load this piece up, you know, what are we looking at? And we can record that. All right, so if you're going to do a report of the device you designed, you know, sometimes this is kind of a really interesting way to do that. And so you can go ahead and record it and, you know, save that for later. But the really, really, really cool part about this, and your kids will like this, because as the projects get more complex, the engineering reports get a little longer. And one of the things that we saw Monday was like, okay, there are elements in each of the pieces that we can pull together in the engineering report. And so we want to tell people that we did some analysis. So I'm going to create a report. And all right, so this is a simulation report on a beam. It's got my name in here. It's pre-populated with, you know, all the stuff that I put in there before. It's got my company name. It's got today's date, a 10 by 10 millimeter plastic beam to see if the strength is enough. And then we'll add something in here, you know. All right, so we type in whatever we want to type in, and once the report comes out to us, then we can take that and you know, continue on. And then it's going to save it, and you got a choice of a web page, because sometimes you want to publish things online, or you could do it in Word format. And it's not Word 97 to 2003 or Word 2007. It's just Microsoft changed the extensions and which program can open what things. So I'm taking the Word 2007 version here. So you click on Create the Report, and it thinks about it for a second. Still thinking about it for a second. Okay, and of course it's on this screen way over here. So here's the report. All right, so it's got my company and it's got my name and it's got today's date, you know, the software used, the solver used. It's got a table of contents for us already. It's got the introduction, which is my 10 by 10 plastic beam. You know, let me just, all right. So model information, well, it was called part 1 because I didn't give it a name, but if I had given it a name, and it's the study properties. All right, so we did a mesh type was tetrahedral, study type was linear static. We set that on the way in. The solid name was called part 1, you know, original name, never find it again. It's got the ABS plastic high impact material that we selected. It gives us the density. So these are all the coefficients of the material that we pulled in. The loads that we put on it. So here's our 2 times, you know, so our 2,000 Newton meters. And some of the constraints. So we had a fixed end and we had a pinned end. All right. DOF stands for degrees of freedom. How much can it move? And it's saying it can't move. All right. And then it gives us results. You know, right? So translation of things. All right. So it's got the graphics from what we had, and it has the stress results. It's got the flexion results, factor of safety results. And, you know, then we come down to the conclusion and then the disclaimer saying like, well, yeah, you used the software to do this, but, you know, you're still responsible for it, you know. So that means that the people who design the software that do this for us don't want to be sued. So it's like on you to verify all these things.